Here we have a video animation illustrating the relationship between a rotating phasor and a cosine plot. On the top here we have a phasor plotted on a typical polar plot, and we've got some quantities about that phasor value that we can adjust. First, we could adjust the phasor amplitude, which is just the length of the vector here. We could also adjust the phase degree, which is the initial angle that this rotating vector here forms with the positive axis here at time t equals 0. And then finally we've got the phasor frequency. This one's new, we haven't seen it before because we haven't seen a rotating phasor, and how this manifests is the speed at which the vector rotates on this polar plot. So I'm going to change some of these quantities. I'm going to change the amplitude and the frequency so we can see how they manifest in this diagram. I'm not going to mess with the phase degree because it doesn't have anything to do with a system that exists of only one phasor quantity. Remember that the phase relationship is between two signals, and since we're only representing one signal right now, we don't have a reference signal with which to compare it to. It is its own reference, so we'll just mess with amplitude and frequency. So the amplitude, as I stated just a second ago, is actually the length of this vector. I can increase the amplitude. You can see that the vector is increasing, right? So we will call that the length of the vector or the magnitude of the vector. So typically in a power systems application, this represents the magnitude of the voltage or the current wave, the peak value. More frequently though, this will represent the RMS value of the voltage or current wave. In this video, it represents peak value though. Because we're just talking about phasors and not actual power system quantities. So I'm going to set that back to 5. We can see the effect there. So we've got a vector, some sort of vector quantity that's got an amplitude of 5. Next, we're going to adjust this frequency value, and the frequency is related to how fast this vector is spinning in a counterclockwise direction. This vector is spinning currently at a rate of 0.1 hertz, and we can see what happens. I'll increase that to, let's say, 0.5 hertz. It's going to spin much faster. So that is 0.5 hertz is 0.5 cycles per second. So we can see that this thing is rotating at that frequency. It takes 2 seconds for that vector to rotate. So that's 0.5. I can change it back to 0.1. Slow it down a little bit, etc. So this is related to the omega term in the cosine function. Remember, omega is equal to 2 pi f, and this is the f term there. It relates to how fast it is spinning. So really what I wanted to illustrate was the relationship between this spinning vector and the cosine plot. You'll notice, and you probably have already noticed, that there is a second vector being plotted on the polar plot here, this other red line that alternately increases in the positive real direction, decreases to 0, then increases in the negative real direction, decreases back to 0. And what that is that is a projection of this rotating vector onto the x-axis. So how much of this rotating vector is pointing only in the x direction. So I'm going to try to time my speech with the rotating vectors. So right about now, all of this vector was pointing in the positive x direction. So we had a big magnitude in the positive x direction. Now none of it is. So we see that this little red vector went to 0. So 0, -5, 0, +5, 0, -5. I think you get the point. What I've done in this plot down here is I have taken the amplitude of this vector that's showing up purely on the real axis, and I've plotted it as a function of time. So as this video progresses, I'm just plotting the magnitude of this vector right here, right here. What interesting thing do we see? A cosine graph shows up. If I plot the magnitude of this function as a function of time, magnitude of this vector as a function of time, I get a cosine graph. So that's one of the ways that we can define cosine. it is the projection of a rotating vector onto the x-axis. I can see that the amplitude of this cosine function is the peak value is the same as the magnitude of this vector. The instantaneous value of this cosine is the same as the projection of this vector onto the x-axis, and the frequency of this cosine function is the same as the rate of rotation. So now what I want to do is I want to change these values here, and let's observe the changes on the cosine plot. So the first is, and there's some small hiccups in this video because of the way I coded it, but the first thing is that I want to go ahead and I want to change the amplitude. So let's change the amplitude to 10. We see the change up here. The associated change right here that we're seeing is that the amplitude of the cosine waveform also changes to 10 to minus 10. Right? So the amplitude of this vector is reflected in the peak value of the cosine waveform. Well, what about the frequency of this? So let's go ahead. I think we had used 0.5 previously, so let's go ahead and up that frequency to half a hertz. And again, there's going to be a little hiccup as the video catches up with the math. But what we can see is that we get a nice higher frequency sinusoidal signal. Nice, the frequency of the cosine increased, right? The period has shortened here, so the frequency went up. And we can visually see how much faster that's spinning there too. So hopefully by viewing this video, you can understand the relationship between a rotating phasor shown on a polar plot and what we're more commonly used to seeing, which is a cosine graph of AC waveform as it relates to voltage and current. And now hopefully you really understand that these two plots are really just ways of representing the exact same information in different formats.